Good afternoon, everyone, and thank you so much for joining us on this somewhat damp afternoon here in Castine. We appreciate having a great turnout. Welcome everyone here in-house and everyone on Zoom to the Wilson Museum, where we reside in the homeland of the Penobscot Nation and their Wabanaki relations. I will ask folks to make sure that any of your electronic devices are silenced or on do not disturb mode, so we don't hear dinging during the course of this afternoon's program. And I'm excited to welcome Dr. Brenda Hall, who's on the faculty of the glacial on the professor of glacial and quaternary geology at the Climate Change Institute at the University of Maine. Dr. Hall studies past glaciers and climate change from Greenland to Antarctica, and the causes of ice ages and rapid and millennial scale climate change. One of a series of wonderful programs that we're being able to tap into the great resources of the Climate Change Institute at the University of Maine and hear from some of their folks. It's been really wonderful. Your program this afternoon is made possible by the generous support of Bangor Savings Bank, who support our entire Connecting to Collections program series that we had going on primarily during the off season to welcome those of you who are here, not just in the beautiful summer days. So thank you, everyone. And I'm going to hand it over to Dr. Hall.
Thank you. Thank you very much for the invitation to come here. And thank you all for showing up. It's great to see such a large crowd in the middle of a Monday afternoon. I think it's Monday. So today I'm going to talk a little bit about the glacial history of Maine. And I'll start out first, though, with a sort of broader scale discussion about ice ages. So we'll have a little bit about ice ages in North America, and then we'll focus in on Maine, look at the glacial history of Maine. And then towards the end of the presentation, I'll show some information about Maine's Ice Age Trail, which some of you may know about, but others may not. It's a ecotourism trail where it's self-guiding, where you can go and look at some of these features. And so I'll show information on that. We'll start out with ice ages in general, and just to set some context for the glacial history of Maine. And so this is a graph showing how climate has changed on a large scale over the last 800,000 years or so. So today is over here, and then this is going back in time, 800,000 years. And this axis shows both temperature, it shows sea level change, and it relates to the amount of ice on land. Okay, so today we're up here. So it's relatively warm. Despite having an Antarctic ice sheet and a Greenland ice sheet, we actually have very little ice on land compared to what would have existed 20,000 years ago. And so this is our present interglacial period. But as you can see from this diagram, it's really an anomaly in this last 800,000 years. And that most of the time, the Earth is spent in what are known as glacial periods, where there's a buildup of ice and temperatures are decreasing. And so this graph shows what's known as the sawtooth pattern of ice ages, where there are interglacial periods. So here's today, here's the previous one about 125,000 years ago, and there are other interglacials back in time, but most of the time is spent with ice building up and temperatures getting colder until it reaches a glacial maximum. And this is when ice covers Maine during these glacial maxima. And so today we're going to be talking mainly about this time period, roughly 20,000 years ago, when Maine was under about a mile of ice. So this sort of sets the stage. Ice ages are repetitive features that occur roughly every 100,000 years. And during each of those, there is a glacial maximum during which ice is coming down into these latitudes. Before I move on, I just want to mention that if you have any questions throughout the talk, feel free to interrupt me. If I say something that isn't clear, jump right in there and ask. I don't mind questions during the presentation. This is North America during the last ice age. So one of those cold periods, let's say roughly 20,000 years ago. And it looked a lot different from today. The major difference being the presence of these large ice sheets. So the Laurentide ice sheets actually was the largest ice sheet on Earth at that time. It was larger than the Antarctic ice sheet is today. So a huge amount of ice. It extended all the way down into southern Ohio, so about 37 degrees latitude, pretty far south. extended up to the Canadian Arctic and joined with an ice sheet that existed over the Rocky Mountains in Western Canada and in the western part of the United States. And you can see Maine is right here. So we were under a substantial amount of ice at that time period, roughly a mile or so. And that ice sheet extended all the way out to the edge of the continental shelf on George's Bank. Okay, so the entire Gulf of Maine did not exist 20,000 years ago. It was under an ice sheet. And as we'll see a little bit later, the sea level was different then too, so the whole geography was different. Now, not only did ice expand in North America and in Europe and around the world during the last ice age, but the climate changed substantially, which resulted in changes in the vegetation zones. And so right up against the ice sheet along most of its margin, there would have been tundra, like you would see in Alaska today. There would have been the megafauna, the mammoths, and so forth that it lived on that sort of tundra. And then just a little bit farther south of that, you'd start getting into the boreal forest, which today, of course, is in Maine. And so all of the climate zones were shifted south and even compressed. We look a little bit closer here at Maine itself. So here's a map of New England and the Canadian Maritimes. During the last ice age, this ice extended from Canada, from the Laurentide ice sheet from Canada, across Maine, and then ended out here in the Gulf of Maine on George's Bank. And this line here, this blue line, is actually the end of the ice sheet, the margin of the ice sheet. And we know it was there because on the seafloor, you can find what are known as moraines. And these moraines are ridges produced by the glacier either pushing material up or dropping material off it. And so if you look at sonar imagery or any other kind of imagery out here on the shelf, you can actually see the moraines from the last ice age. They also come back on land though, because Martha's Vineyard, Long Island are all part of that same moraine system. And so it marks the former footprint of the ice sheet. So this was about 20,000 years ago. After that time, the ice started retreating quite rapidly back towards the present coast. At the same time, which might not think about at first, ice also began retreating back this way. And it's not on here, but this is the St. Lawrence River up here in this region. And what happened was that ice, when ice began to retreat, it retreated not only from the Gulf of Maine, but also up through the Gulf of St. Lawrence and ended up cutting Maine off from the rest of the ice sheet. And so all of this would be deglaciated before Maine was. And so for a little while, we had our own little ice cap in Maine, called the Maine Ice Cap. And it was centered right in this area here. It existed probably 3,000 or 4,000 years before finally disappearing about 13,000 years ago. So, many of you are familiar with this. This is Katahdin. The ice sheet covered Katahdin during the last ice age. And so, it's almost a mile high. Ice was over the top of it. So everything there would have been covered by ice. But during deglaciation, or during the time when the ice started melting, Katahdin emerged from the ice sheet. So you can think of the ice sheet as sort of lowering around it. And so this would have been what's known as a nunatak, and a nunatak is simply an island in the middle of a glacier. It's a piece of rock or a mountaintop that's starting to emerge from the ice. And so Katahdin would have been a nunatak at that time. It would have been emerging from the ice sheet. And the ice continued to thin all down around it, down to the lowlands. Some of you may have been up in these. These are cirques. So cirques are basins that are carved by glaciers. They're not carved by ice sheets, though. They're carved by alpine glaciers. So glaciers similar to what you'd find in the Western United States or in the Alps of Europe. So at one point in our distant history in Maine, we had alpine glaciers, which is pretty neat, actually. At least I think it's pretty neat. But we don't know when that was. We have no idea when that was. it was sometime before the last ice age. Okay, we know that the last glaciation here was not from little glaciers here in these cirques, but rather from the big ice sheet that was covering them up. But at some time in the past, who knows how long ago, there used to be alpine glaciers. Yeah.
So you're saying that Maine was covered by a glacier that was a mile deep. Katahdin's a mile high. How do you know that Katahdin was covered by the glacier?
Right, right. Okay, so a mile thick is an estimate. It was probably a bit more than that, but yes. So we know Katahdin was covered by ice because you can find what are called glacial erratics. And these are rocks transported by the glacier, and you can find rocks transported by the ice sheet on top of Katahdin that are not of the same rock type as Katahdin. And so we know that the ice was up there. Yep.
Are there any other things like polishing and striations, or just
not a lot on the summit of Katahdin. So the summit area and the tableland is very broken up. I don't know how many of you have been up there. Okay, some of you have. Yeah, it's all like jagged rocks and it's broken. That forms by what's called periglacial weathering. In other words, freeze thaw. And so if you have a lot of freeze thaw going on, that tends to destroy things like striations pretty quickly. Yeah, and so really we have to rely on things like, you know, the presence of rocks that came from somewhere else that could have only gotten there by the glacier.
Yeah. So is the rounded appearance of Katahdin due to the sandpaper effect of the glacier moving across it, or is it just from because it's so the mountains here are so ancient, it's from old weathering?
That's a really good question, and the short answer is we don't know for sure, but definitely the ice sheet would have rounded off some of the sides of the mountain. The other thing that happens is that there really is a lot of freeze thaw and weathering that goes on there even today, and so I think that contributes to things like reduction in slope angles and so forth. So, so it's probably a combination of all of those. Yeah.
I was just trying to understand what the difference was about the alpine glacier versus.
Yeah, so they're just a different kind of glacier. They're a smaller mountain glacier. Why they used to exist in the past and didn't during the last ice age is they probably date to a time period before the ice sheets used to get so big. So there may have been a time many glaciations ago when it was cold enough for there to be small glaciers on the mountains here, but the ice sheets did not have enough time to grow to get all the way to Maine, perhaps. They're a bit of a mystery, actually. And Katahdin's not the only mountain in Maine with cirques. There are many mountains in western Maine that have cirques. The Crocker Mountains, for example. Also over in New Hampshire, Mount Washington famously has cirques.
Tuckerman's Ravine.
Yes, Tuckerman's Ravine. Yes. I mean, they're spectacular features, but their age is not known. Any other questions on this? Yeah.
So, what triggered these ice ages throughout every 100,000? I have a question.
Right. Okay.
And,
So, getting right to the meat of it here. What triggered ice ages? That is $1 million question. It's actually a question that people have been trying to answer for 200 years at this point. The leading hypothesis is that they are related to changes in the geometry and shape of our orbit, and the tilt of the Earth on its spin axis, and how much it wobbles when it spins. And all of those things together alter the amount of sunlight that reaches different places on the Earth. And the idea is that when the eccentricity, which is the shape of the orbit, the tilt of the Earth on its axis, and the wobble, when those all align perfectly, you have times when it gets really cold in summers. And the leading hypothesis is that when it gets really cold in summers in the northern hemisphere, ice builds up and persists throughout the year, and you start an ice age. So if you were to look in any book and look online, that's the explanation you would probably find.
So we're in the opposite end of that, and, you know, man's influence on global heating and all that. So will it at some point trigger? Is it man influence, or is it just what you described as far as the rotational, you know,
Right.
aspects of the earth and all that? Or is it a combination?
Yeah, so those are two different things. I mean, the sort of human-induced change is sort of one thing. The ice age cycles is something else. But they may interact. So the last ice age ended about 13,000 years ago, but the cycles are continuing, and we're at the stage now where we should be starting to go back down to the next cold period. That buildup. Actually, if we just back up here, you see these interglacials are pretty short. They're just these spikes, and then it starts to get cold again. We should be at the point where we're starting to get cold again, because northern hemisphere summers by this mechanism are starting to cool off. Whether or not that will be enough to prevent us from, whether or not global warming will actually prevent us from dropping into another ice age is not a question that I want to speculate on, because there are a lot of different components of the climate system, and we don't understand them. We don't understand whether if our effect on climate nudges the climate system in a certain way, we may get a result that we're not anticipating. So
If these are just, if it's affecting the northern hemisphere, you said it affects the northern hemisphere, does that mean that ice ages are asynchronous between the northern hemisphere and, say, Patagonia and
another excellent
Savannah?
question. Excellent question. So I said, I mentioned that would be the explanation you'd find in most books. However, yes, you can't explain southern hemisphere glaciation. So they're called orbital parameters. These factors that combine to change the amount of sunlight that reaches Earth actually are opposite in the two hemispheres, because the hemispheres experience seasons at different times. So by that hypothesis, you cannot explain ice ages in the southern hemisphere, at least not synchronous ice ages in the southern hemisphere. But ice ages are in fact synchronous between the two hemispheres, which means there's a major flaw in that hypothesis. And that's where we are, unfortunately, in terms of understanding it. It's an area of active research. I work in South America a lot for that very question. I'm trying to understand the relative timing of ice ages and all climate changes between the hemispheres. So there has to be some mechanism that makes the whole globe go into an ice age at once, and we're not quite sure what that is yet. There are ideas, but all right. Any other questions on this? Back to Maine. All right. So Katahdin was probably the first place to come out of the ice in Maine, although a lot of people talk about some of the high mountains on MDI as potential places, Cadillac, Sargent Mountain, and so forth. Along the coast of Maine, around here, I imagine, and also on MDI and further east, you find a lot of what's called aerially scoured terrain, which is an area where the glacier has stripped off a lot of the pre-existing soils and weathered rock. And so you see a lot of bare bedrock, a lot of hills that are well, you have good views from the hills. And you can also see, these are glacial erratics. So I mentioned for Katahdin that there are erratics in different places from different locations. That's how we know the ice covered the top of the mountain. Same here. And so you might be able to see there are color differences. There are these white rocks, and then there are the pink rocks, pink bedrock. And so this is pink bedrock. Any of you have been down here? It's the Cadillac mountain granite. It's this beautiful pink granite. But these white rocks are not. Those are brought from the Lucerne area. And so these are examples of glacial erratics and things that you could find that are transported by glaciers here. Just some other examples of glacial landforms. This is looking down Jordan Pond. It's a glacially carved valley, or a trough, sometimes called. Soame Sound is parallel to this, and it's a fjord because it's flooded by the sea. This one is just above sea level. In fact, there's an old marine delta out here, actually, when sea level used to be a little bit higher, that you can find. This lake is actually dammed by a moraine. So there's a moraine here right sort of behind the Jordan Pond house. And it's just a classic example of a large-scale glacial erosional feature in this area. Looking the other direction, these are boulders from that moraine. This is looking towards the bubbles. And so these are classic examples of glacially molded hills. And so very often in Maine, you'll see hills that have a more gentle slope and then a steep cliff slope on one side. These are called roche moutonnee, which is a fancy term that actually means sheep rock or something like that in French. But basically, these are formed by glacial erosion. So on the up glacier side, the glacier is in really good contact with the bedrock and is abrading it. And so if you were to go up the gentle side, you would find striations, you'd find these things called crescentic gouges, which look like little moon-shaped things that are chipped out of the rock. So you see all that sort of evidence. But then suddenly you get to this cliff side and all of that disappears. Instead, you've got a lot of jagged, broken rock. It's very steep. And that used to be a cavity under the ice. What happens in these cavities is that water can get into these and it freezes. The cavity is an area of low pressure and that water will freeze. And as it freezes, it grabs hold of rocks. It gets into cracks and it sort of wedges the cracks open as the ice expands. And the ice sort of adheres to the rocks. If you can think about like sort of slushy snow, when it freezes, anything that slushy snow is in contact with sticks to it. The same with the glacier, essentially. It adheres to the rock, and as it does that, it pulls it away as the glacier moves. And so this is a side of the mountain where you get what's called plucking, where the glacier takes big rocks and moves them away. Okay, so that accounts for a lot of the asymmetric hills that we see because they have a shallow up glacier side where it's in good contact with the bed, but then as the ice comes over the obstacle, it can't get right back down onto the bed. It's not flexible enough to do that. And so there's usually a cavity, and where you have a cavity, water can get into it and it generally refreezes and causes this plucking. So they're all over the place in coastal Maine and western Maine. Yeah.
If the glaciers retreating towards the north, would that mean that the gradual slopes are on the north side and that most of the cliffs are facing the same direction?
Right. So the gradual side is always the direction the ice is flowing. And so
The ice is flowing, so that's when they come down.
right. So even when the ice is retreating, it's still flowing in the same direction. It's just melting back faster than it's flowing. Yeah. Yeah. So in this picture, the ice would have been flowing more or less like this, sort of coming obliquely towards us a little bit. That all clear? Should we move on? All right. I mentioned erratics. This is a classic one.
Yeah.
Old picture. Yeah, balanced rock up on the bubbles. Yeah. It's a glacial erratic. We had a project down in Acadia, and we sampled rocks for various dating purposes. And the one stipulation by the Park Service was we could not sample that rock. All right, so that's at the maximum. During retreat, the retreat in Maine wasn't steady. In other words, it didn't just march right back to Canada. Instead, it paused at various times and fluctuated. And one of those big pauses produced something known as the Pineo Ridge system. And the Pineo Ridge system is just a big line of moraines, these ridges formed by glaciers, a lot of what are known as ice contact deltas, so places where the ice entered the ocean and started to build up a delta, just like the Mississippi Delta. And there's a whole line of these. And so in orange here, it's showing where that moraine system goes through our state. Okay, so this is the Cherry Field area, just for reference. And then this is going east towards the Canadian border over here. Okay. So early on, the ice retreated and formed lobes and formed these white moraines here. But at some point, roughly 16,000 years ago, something happened to the ice. It reorganized itself. It became healthier for a time, and it produced this really big system. So you can imagine the ice would have been sitting right here at one point. When it was doing that, it was producing a lot of, in addition to those great big moraines, it was producing a lot of small moraines, and it produced them in this way. And so you can imagine the glacier. So here's the ice sheet, and it was in contact with the ocean. And we know this because we can find features such as marine clay in the glacial deposits. We can find shells in the glacial deposits. We can find old shorelines from the ocean, beaches, deltas. And so this is ice that was retreating with the ocean right up against it. And so as it did that, it would be calving off icebergs. And so there'd be what are known as drop stones, which are materials that fall out of the icebergs. Excuse me. And those fall into the ocean, into the marine mud. And it's also building one of these end moraines, one of these moraines here, right at the position where the ice starts to become afloat. And this is made up of a variety of materials. Some of it's quite coarse grained, some of it's a little bit finer towards the ocean side. But wherever the glacier is pushing forward and pushing forward just a little bit into the ocean, it forms one of these small moraine ridges here. And these are a very common feature of coastal areas of Maine. This is an example of one. This is down near Cherry Field. This ridge right here with all the boulders on it and the blueberry field here is one of those moraines. And it's so sometime 16,000 years ago or so, there would have been a glacier depositing this feature here. Here's just another example of one. So ridge this direction. You probably have seen these. They're all over the place. There are hundreds and hundreds of them. In fact, there are an awful lot of them. This is what's known as a Lidar image. And Lidar is using laser, either from a plane or a satellite. And it actually is able to see the ground surface. You can make a correction to get rid of the effect of vegetation. So you can see the state for the first time, really, with Lidar. You can see the glacial features. And these stripes here that you see, every one of these stripes is a moraine, like those pictures I just showed you. And so you can trace the former ice margin, all along each one of these.
So they're pretty much east-west.
They're pretty much east-west because the ice margin would have been east-west, and it would have been retreating back to the north. And so the moraines here are older than the moraines up here. So this is representing retreat of ice back in this direction. Each one of those represents where the ice used to be.
What's the distance between those?
It's anywhere from a few tens of meters to a few hundreds of meters. And there's some suggestion these may be annual features. Because what happens with this type of moraine is that the glacier advances in the winter when it's colder and it gets a lot of its precipitation, so it will advance forward a little bit and produce this moraine. It'll push the sediment out in front of it. But then in the summer, it melts back. Now, if there's an overall glacier retreat, when it advances the next winter, it doesn't get quite as far as it did the winter before. And so the next ridge is a little bit behind it, and so forth. And so it's thought, anyway, that each of these is representing a year of the ice retreat. So you can track rates of ice retreat that way, if that's the case.
What's the little tongue off of? I can't read that. Something Cove?
Salisbury Cove.
Oh, the little tongue sticking out there. Right there, yeah. Is that a glacial feature or just a happy coincidence?
I would guess it's probably bedrock,
Yeah.
although it has moraines on top of it.
Mm-hmm.
So there's now Lidar for most of the state, and it's fantastic. You can get it on, there's a state website that's it's moved, or else I would tell you that the name of the state website used to be the Maine Office of GIS. It's called something else now. But there is Lidar available for the whole state, and it's for my purposes, it's amazing because you can see features that nobody has seen in probably 13,000 years when we became covered with trees. But it's also useful if you're interested in, like, I don't know, like historical stuff. So you can see old stone walls on it. You can see cellar holes. It has a lot of interesting features on it. So you might want to check that out if you're interested in it. So, so I mentioned the moraines would be formed at the margin of a glacier, and I just wanted to show a picture of what it might have looked like. This is not Maine. This is in Antarctica. So this is a big ice sheet, the Antarctic ice sheet coming out into the ocean here, taken by one of my students, Scott Erratic. And this will also have a moraine forming under the water there, just like the ones in Maine. And so this is more or less what the coast of Maine would have looked like during deglaciation. Okay, so I mentioned that this is a big moraine system, and it also has some deltas. And so I just want to show briefly. I don't want to show too many pictures of deltas because they're just flat. But this is so the blueberry barrens down near the Cherryfield area. This flat surface here is an old glacial marine delta. So the ice would have been in contact with the ocean, and as it was in contact with the ocean, all of the meltwater that came off the ice was bringing sand and gravel and mud and dropping it in the ocean in front of it. And over time, it actually built up to sea level. And we look at a sort of a diagram here. This is what would have happened here about 16,000 years ago. There'd be the ice, there's the ocean out here, and the ice put a lot of sediments into the ocean, which caused a delta to form out in front of the ice sheet. And at some point, there even would have been meltwater streams running across that delta out into the ocean. And so if you go to a place like Cherryfield or some of these other features, there are deltas in Franklin, Ellsworth, there are lots of them. Sometimes you can see the old river channel on the surface still. So this is, I want to point out, this is Dr. Hal Borns, the late, unfortunately, Dr. Hal Borns. He was my predecessor at the University of Maine, and it was his idea to come up with something called the Maine Ice Age Trail. Who's heard of the Ice Age Trail before? A few of you. Okay, great. And so this was his idea as a way to bring people into Eastern Maine and to educate them about the landforms that we've got in the state. The glacial landforms that we have in Eastern Maine are some of the best examples in the world of some of these glacial marine deltas, such as this, and some of the Eskers, which are these ridges of sand and gravel that formed under the ice. And so he created what's known as Maine's Ice Age Trail, which is a printed map available at the UMaine bookstore, but you can also download it online. And on this, it has, you can probably see all these little purple dots. Those are mammoths. Those are all stops. And so you can go to these stops. There's some description of the features that you're looking at. And you can spend a couple days looking at these glacial features. So there's a website, which if any of you are interested, this is where you would go to find it. And on that website, it has some general information, some background about the Ice Age in Maine. It's got stops for the trails, has the map. you can get it. And there's also an app if you have an iPad and want to take that along.
How far, what's where is it, how far south does it go?
It starts on Cadillac Mountain and goes east to the Canadian border. Yeah. All right. And so if we just look at it a little more closely, if you go to the website, these are all the stops. So you can see how they're clustered over to Eastport here, Cadillac over here. And so you can go on there and click, and you'll get all the stops, get a variety of stops. And then if you want to just pick one, let's pick stop 42, West Quaddy Peat Bog. There'll be a location, a description of the geology and why this is an interesting area, pictures and so forth, which you can look at a little more closely. So this is one of the stops. This is, so instead of a landform, these are sediments to look at. And so the very bottom, which you can see at low tide here, is the glacial marine clay from the deglaciation of Maine. If you were to look at it and look at the shells in it, they'd be of species that don't live here anymore. They'd be ones that you'd find in southern Greenland today. And then there's some other deposits on top of this. There's sort of a swampy deposit with old pieces of wood in there from, I don't know how old they are, but they could be, I don't know, 10,000 years old or so. And then there's a peat bog on top of it. And so this is just an example of the types of stops that you can go to. And there are videos too. So here's Dr. Bourne's describing this particular spot. Just another example. So I showed this map before. The deltas were over here, and I didn't really talk about these red dots, but those are eskers. Now, eskers are sinuous ridges of sand and gravel. They actually are an important resource. We use them a lot for drinking water aquifers. We use them for sand and gravel for building and so forth. They would have formed underneath the ice in a tunnel. And so glaciers, most ice sheets, have subglacial water drainage. So there's actually a lot of water at the bottom of ice sheets. And sometimes that's in tunnels, and so there are big rivers that are coming out of the ice. And eskers are the deposits that form in those rivers. That is the esker on the Lidar image. Several miles long. They're these steep-sided hills, steep-sided ridges. And this is what a tunnel looks like under a modern glacier. So this is a river coming out of a tunnel in the ice. And so each of our eskers in Maine would have formed in that manner. There would have been tunnels under the ice. So what happens is in these tunnels over time, sediment builds up and it fills the tunnels. And the tunnels, as long as the water is flowing, they keep enlarging a little bit. And so it can build and build and build. But eventually, deglaciation happens or the water switches locations, and you're left with a lot of sediment filling this former tunnel. And when the ice retreats, you have this very steep-sided ridge that follows the path of the former river. So I'm trying to think of other examples. There are a lot of them in the Bangor area. A lot of these eskers, one that goes right through the Mount Hope Cemetery in Bangor. There are lots of them in eastern Maine. You can usually tell because you suddenly come up on a very narrow ridge where you look down on both sides of the road, it starts dropping off pretty fast. Usually it's covered with pine trees or something similar because it's very well drained soil, sand and gravel, and you won't see any big boulders around, so it's not a moraine. And so those give you a hint that perhaps you're on an esker. And again, the ones in Maine are some of the most famous in the world. It's called the Katahdin Esker system, and people come from all over to see it.
We have a question on Zoom that was, why was Alaska not affected that much from the last ice age?
Why was Alaska not? Yeah, so you may, I don't know if you looked at the image I showed of the North America right at the beginning of the talk, but Alaska wasn't covered by an ice sheet. The mountain glaciers got bigger, but there wasn't a big ice sheet over Alaska. The reason for that is thought to be because it was too dry. So you need two things to form glaciers. It has to be cold enough, but it also has to snow enough. And it was thought that Alaska was just simply too dry, especially with sea level would have been lower at the time. There would have been the Bering Strait land bridge exposed above sea level. And so a lot of the moisture that you might get in there today didn't get in there during the last ice age. More Esker pictures. So this is when we're going through the lake there.
Are Eskers predominantly perpendicular to moraine brows?
For the most part, yes. It may not be exactly perpendicular. It could be a little bit of an angle, but yes. So if you've got, yeah, you'd have the ice margin, which would be represented by the moraine, and then the esker would be coming more or less perpendicular to that margin. One of the neat things about eskers is that they, because the water in these tunnels is pressurized, eskers can go up and down over hills. So, which is neat because the water in glaciers can go up and down because it's pressurized water. All right, and one last stop. Just looking at the time here, and then we'll wrap up after this. So this is a familiar view for probably most of you from the top of Cadillac. There are a lot of things you can see from the top of Cadillac Mountain. The other thing that you can see on top of Cadillac, which takes a little bit of doing, but if you have time, it's worth doing if you're interested, is that you can see glacial polish up there. Glacial polish is pretty rare to see. It's something, so if you imagine the bed of the glacier, it's sliding along its bed, and there's a lot of fine-grained gritty material at the base as well. And so if you've got a glacier sliding on gritty material, it's going to form striations, but it's also going to polish the bedrock surface, just like if you were, polishing a rock in a rock shop or something. And so polish is like sub-millimeter thickness. I mean, it's just this fine sheen on the surface of the rock, so it doesn't preserve very well over time. But on the top of Cadillac, if you walk around on some of the paths there and look sort of walking into the sun, you might see some of the bedrock start to glint and shine. There are little patches of it left. Most of it's been eroded away, but you can see little patches of it, and that's glacial polish. So that's something that is pretty neat about this site. So I think we've come to our time here. So thank you all for being here. This is that link again for the Ice Age Trail. This is another interesting one from the Maine Geological Survey, where they have sort of photo slideshows and little brochures on not only glacial history, but on things like fossils and minerals in Maine as well. So those are worth looking at if you're interested in this. So thank you very much.
So, quick question. I go kayaking with the group here and there, and one of our trips goes out of Naskeg around Harbor Island and around Hog Island. And in one of the coves on Hog Island, there is an enormous glacial erratic.
Wow.
It is gigantic.
Uh-huh.
And it's almost like a square or rectangular loaf around. So I kind of wonder what that glacier did. The glacial erratics get set down gently, or can they drop out of the glacier?
So usually it's gentle, because if you can imagine, the ice is just slowly melting around it. In fact, it's so gentle, sometimes you get big boulders perched on little boulders, called perched erratics. But one thing, so it's possible that cracking occurred while the rock was in the glacier, just because of the pressure, or even as the pressure was released if you imagine a rock under very high pressure, and then as the ice melts around it, all that pressure is released, and so it may have fractured because of that. We can't eliminate the possibility that it also fractured later on after it came out of the ice, just due to right, or just freezing and thawing at some point. But rocks do fracture in the glacier or during, when they melt out of the glacier because pressure changes.
Could you give a few examples of your methodology, of the kind of the epistemology of how you do the research, the location, tools, things like you mentioned Latin America, South America?
Right. So it depends on the question we're asking. But so, for example, I'm involved in projects studying the origin of ice ages. And one of the things we're interested in is whether or not they're globally synchronous. And so a lot of our work is in the southern hemisphere, because that's the area that it's just been really hard to explain why there are ice ages there, or at least synchronous ice ages. We do a lot of mapping of glacial deposits. So we'll first thing we do when we get to a landscape is we'll start finding the moraines, the Eskers, and putting them onto a map, so we have a picture of where the glacier used to be. But in order to make that picture useful, we need dates. We need to know when it was at a certain place at a certain time. We need to know how fast it got from point A to point B and things like that. And so there are really two methods we use for dating landforms. First one is pretty common, radiocarbon dating. Probably everyone here is familiar with that. It involves finding organic materials in the glacial features. Something like maybe the glacier overran a forest. You might find logs sticking out of the moraine. That would be the ideal situation. Doesn't happen very often. If you could date those trees, you would know when the advance of the ice took place. So we use radiocarbon for things like that. We also use a newish method developed about 30 years ago called Cosmogenic surface exposure age dating. And that's a mouthful, but basically it means we can date rock surfaces. We can date the amount of time a surface has been exposed to the atmosphere. So if you imagine there's a rock in the glacier, when it's uncovered by the ice, it's suddenly exposed to the sky. And cosmic rays come in from outer space, and they come in all the time. We're being hit by them right now. Those penetrate the surface of the rock a little bit. And when they do that, they actually cause reactions within the rock, reactions within the minerals. And so something like an oxygen-16 atom can be broken up into smaller bits and pieces. One of which is beryllium-10, which is the isotope that we use. And it's produced only in that manner. This new cosmogenic isotope, this beryllium-10, is produced only because of cosmic rays hitting the rock. And so all of the beryllium-10 in that rock is from the amount of time it took since the glacier uncovered the rock. So if you know how fast this process takes place and you can measure what's in that rock now, you can back calculate how much time that rock has sat at the surface. It's a fairly long process, long and complicated process, but it allows you to date landform surfaces and determine how old they are. So that is probably one of the primary methods we use. We actually have a cosmogenic lab at the University of Maine where we do this process, where we do the chemistry for this process. The actual sample is very tiny at the end. Once you've gone through all the chemistry, a piece of granite goes into the lab and it comes out as a cathode, essentially, with a tiny bit of beryllium in it that gets sent to an accelerator laboratory for measurement. A lot of field work, a lot of laboratory work.
Were there any glacially dammed lakes in Maine that were big enough to leave the signs on the land after the outburst flood, like the Scablands in Washington?
Nothing that I know of that produced outburst floods on that sort of scale. Or
well, that was a pretty big scale,
right? Or at least I don't know of any outburst flood locations in Maine.
Okay.
But there were large ice dammed lakes, and there probably were some outburst floods. There actually, to back up, there is one place, there was at one point a glacial lake up sort of near Flagstaff Lake today in western Maine. And that one may have outbursts because you see a change in the sediments coming down the Kennebec River at that time. But there were a lot of ice dammed lakes, particularly in northern and western Maine.
Okay. And then my second one is looking at the mammoth. Are there any Pleistocene remains around Maine of the animals, or was it not a hospitable?
There have been, there's at least one mammoth
Okay.
found in Maine, in the Scarborough area. But there would have been other Pleistocene megafauna, big animals, during the initial deglaciation.
I live on White Pond, and I don't know if you know where it is. It's north of here in Penobscot. The entire perimeter of this long pond is covered with huge boulders that go even into the water. And I always wondered whether they were erratic, but I don't know enough about geology to be able to tell whether they're different or not.
Yeah.
But it's sort of like in a basin, where it's a watershed from surrounding area. And some of them are cut in half by they're split, but some of them are really pretty big.
Yeah. So I haven't been there, so I don't know, but I would guess I would guess that most places you find lots of big boulders. In this area, they would be glacial in origin originally. It's possible that they were later reworked by the ocean, because actually the ocean used to be, I didn't get to that today, but the ocean used to be higher than it is today. And then the land rose back up out of the ocean. But the origin of those boulders probably, at least originally, was glacial. Brought by the ocean.
It does have a creek that goes into Northern Bay, so I can picture that it would have been had ocean.
Yeah, I would say probably glacial originally.
Thank you.
They may have been modified since, but good question.
Do you have a sense at what point in the deglaciation the land rebound happens?
Right, so it happens as soon as deglaciation begins, and it's actually the fastest right at the start of deglaciation. And so, actually, this is a sea level curve, and intended to show this, but here's today. This is going back in time to 16,000 years ago. Here's today's sea level right here. And so early on, sea level is quite a bit higher than it is today, about 80 meters higher. And that's because the weight of the glacier pushed down the crust of the earth. It weighed that much that it actually caused the crust to sink. And so when the ice receded, the crust came right back up. And so that is represented by this drop, which is the drop in what's called relative sea level. So the sea level appears to be dropping, but actually it's the land that's coming up. And so that happens very fast, within a couple thousand years or so, roughly 12,000 years ago. It actually overshot. It reached a low stand where you could actually have walked out in the Gulf of Maine here to anywhere that was shallower than about 55 meters water depth today. And so there would have been large areas of the Gulf of Maine at about 11,000 years ago that would have been above sea level. But then global sea levels kept rising, but our rebound slowed down. And so the rise of the land out of after deglaciation happens really fast at first, and then it slows down a lot afterwards. And so at this point, it had slowed down a lot, but the global sea level was still rising fast because there were still ice sheets around the world melting. And so that's why our sea level came back up to where it is now.
That's also why we don't find indigenous, the traces of indigenous occupation of our coast is because our coast is out quite a ways from what it is now. So the earliest, during that period, the earliest indigenous occupation would have been in the water.
Fishermen have found
They pull things up, yeah.
Mhm.
Things about what, yeah.
The low stand is post glacial retreat though, because during the glaciated period, wasn't sea level about 100 meters lower now than it
Right,
is?
during the glacial maximum, it was about 120 to 130
Okay.
meters lower. And so, yes, so the low stand, this is after the ice is gone from Maine.
Thank you so much, and yeah, big hand, thank you. Like going back to geology class. Really quickly, a couple of did you knows, which I think are kind of fun. Dr. John Howard Wilson, the founder of the Wilson Museum, did his dissertation on the glacial geology of Nantucket and Cape Cod, and he was working mostly in sock sediments and collecting fossil shells, and we still have drawers and drawers of what we believe are the fossil shells that Dr. Wilson collected during his dissertation research at Columbia. And also the work that went into the Maine Ice Age Trail and the understanding of the geological significance of down East Maine was part of what made the case for Washington and Hancock County to receive their designation as a National Heritage Area. So all of Washington and Hancock County are now National Heritage Area, and that geologic specialness was part of what made the case for that. And then finally, I know it's like one day right after the other, and I know folks have a lot going on, but we have another really exciting program here tomorrow at 6:30, where we've got a panel of folks that work on community resilience to climate change. We've got Roberta Boskowitz from our select board, who's part of the comprehensive plan committee that worked on the climate change part of our comprehensive plan. We have Johanna Blackman, who's from Climate to Thrive on MDI, and we have Alan Krause, who is with Blue Hill Peninsula Tomorrow, which is the Blue Hill Peninsula Community Climate Change Group, similar to Climate to Thrive. So they're going to be here at 6:30 tomorrow in person, also available on Zoom. If you go to our website and calendar, you can register. That's going to be really fascinating to talk about how, on a community level, we can be prepared for and build climate change resilience. So welcome folks to that. Thank you very much.